On Friday, you were introduced to matter, right? We looked at matter and then a bunch of little things that we could do to it. We could change it, we could classify it, we could even classify the descriptions of it with the intensive and extensive. One other thing that I didn't get to that would have fit really nicely in there would be the fact that matter exists in 3 different phases. So for those of y'all at home, pause the video and get our entry slide down. Now, the topics from today are still topics that you should absolutely recognize from past years of your life. So let's start with phases. Solids, liquids, gases. Look at those images that you drew. This will be what I'm referring to as that picture for at home. And you'll notice that for solids, the molecules, they're really atoms. You're not charged for that word yet. Unit 2 is called atoms, so it's coming. But just the smallest little things that make up my solid material here, they are as tightly packed together as they can be. All right, so in a solid, you've got these tiniest particles that exist packed as tightly together as they can be. Do you think they are in any kind of motion at all? They are. They are in constant motion. All matter is in constant motion. However, in solids, the motion is just a vibration. And for those of y'all that are smart and you keep adding little things to your notes while I talk, vibration's a good thing to add here for the solids. But anyway, I'm sure y'all are being good little note takers at home also. Yeah, the solids have this constant, slight vibration between their molecules, but it's so slight that it's pretty much undetectable. But they're moving. What do I need to do to this solid to make it start turning into a liquid? What needs to be added to it? Heat or energy is another way to say it. But yeah, if I take my solid and I start heating it up, the particles start moving faster, right? More energy, more ability to move, more kinetics going on. So if I add energy, it moves faster and faster and faster until eventually they start to roll over each other. And we call this flowing. And this is the movement that you're now able to see because those particles are moving faster. So my liquids have the ability to flow. Hey, what do I need to do to my liquid in order to make it turn into a gas? Keep adding more heat. Just keep on going. Keep pumping in more and more energy, and eventually they'll start rolling over themselves very quickly, the molecules, until eventually they just split from each other and they become these wild little animals that are just floating wildly around whatever space it is that they're occupying. So a way to say it is that when you compare the phases of matter together, that the solids have the least amount of energy while the gases have the most. Speaking of gases, anybody know the most abundant gas in this room with us? Air is a general term for all the gases, not oxygen, not carbon dioxide. Oh, they're going to be the first class that doesn't know. How embarrassing. On the video, too. I won't tell you what class it is. It's 9th period. You don't take one more stab. What is the most abundant gas in here? Ouch. Nitrogen is the most abundant gas. It's about 70%, so it's not even a close race. But the other 2 that you named are good, all right? Oxygen comes in second. All right, luckily, we really like oxygen. And then we are producing carbon dioxide, which is actually not good for us, but it's good for plants. They use it to make more O2. So awesome. Anyway, while those are the gases in the room, here's an interesting thing about gases. And now we're starting to look at some of these ideas about shape and volume. The gases in the room don't mind you changing their allotted space. What I mean by that is if we were to take the oxygen, carbon dioxide, nitrogen, right, there's other gases too, but they're trace, and we were to start pumping the walls in towards each other and closing down the room, the gases would just tighten up next to each other. They wouldn't mind that you're doing it. It would make there be more pressure and other things we're not talking about right now. But my point is that the gases, the single sample of gas, will occupy a smaller space if you ask them to. That's important to point out because the other two phases of matter won't do that. If this room was filled with water instead of gas, like filled to the brim with water and we were just floating around drowned, and we were to do the same thing with the walls, the water would destroy the walls as it tried to do it because you can't push water together. Liquids won't let you do it. The same with the solids. What would the solids in the room do if you closed all the walls in on them? They would be destroyed, right? They would start to break apart because solids and liquids have fixed shapes and fixed volumes that they won't let you change. Liquids have a little more leeway on the shape, though, than solids do. Like if I have my liquid sample here, see my liquid sample, and I were to pour it from this big bulky shape to this more flattened elongated shape, will the water change shape as it pours? Yeah, it will. All right, and I can't show you because if y'all remember on Friday I broke this while I was throwing it and showing you physical and chemical changes. It was my favorite one too. But yeah, if I pour this shape into this shape, it changes shapes. But what it won't change is the amount of space it takes up. There's about 1,000 milliliters here, right? Whether I have it in this shape as 1,000 mils, or I dump it in here into this shape, both of them would still be, according to this single sample, 1,000 mils. So that's why the volume does stay fixed for a liquid, whereas in the gas, again, you can close the gases into a different volume and they don't mind you doing it. You're going to be asked to identify these differences and similarities come exam time. So you will want to make sure that you're practicing. The other thing that comes along with these phase changes is some vocab, but you'll be impressed with the amount of that vocab that you might already know. So let's look. We're going to be looking at this slide slowly. All right, so here's what we're looking at, y'all. There are 6 different ways that one phase can change into another phase. Let's see how many of them you already know. You can apply these words to any substance. I tend to use water because of your familiarity with it. So let's imagine water. But again, all of the vocab that you're about to write down applies to all substances. So let's do water. Solid to liquid. Solid water, what's the common word for solid water? Ice. Yes, you got that one. You're right. You're better at ice than nitrogen, apparently. Yeah, ice. If solid ice turns into liquid water, what did the ice do? It melted, and that is actually a scientific word. Melting is the phase change from solid to liquid. The opposite process is liquid to solid when the water turns into ice, which of course that process is called freezing. Yeah, look at that. You don't even need me. All right, let's move from first grade words to second grade words. Liquid to gas will describe the situation where I pour a little bit of water on the desk and an hour later it's turned into air. What did the water do? Now, while evaporation is fine, vaporization is a better chemistry word, but they're both correct. But vaporization makes you sound smarter. You could even call it boiling, technically. So far, so good? All right. Gas to liquid would be the instance like in the mornings where the air gets real heavy and it turns back into liquid on things like glass and leaves. What do we call that? Condensation. And now can I stump you? The last two are usually new words for you because they both skip the liquid phase. Let's take a look. Is it possible for a solid item to turn into a gas without ever getting wet? Can you think of anything that does it, especially like around Halloween time, or it's the way they make your drinks bubble at Magic Time Machine, if anybody goes there? What is it? Yes, that's it. Dry ice. You'll never play with dry ice? You poor, poor children. Dry ice is frozen carbon dioxide, right? It's negative 27 degrees Fahrenheit, so you can touch it for about half a second, and after that, it burns the heck out of you. But if you have a block of dry ice and you drop it down, it just smokes off. It just looks like just turning into smoke, but it's turning into gas because dry ice can't get wet, right? You can dump water on it, but all it does is it just makes the water around it bubble and turn into gas around it. That process is called sublimation. New good vocab word for you. I have a sublimation video that I've been showing in my classes, but since I'm recording, I can't do it right now like I would. So when we get to the end and I turn this off, I'll show you the video of me doing something stupid with dry ice. I might, if I looks like I'm forgetting when it's over, remind me that I wanted to show you all that video. Anyway, the final one is the reverse process, gas to solid, called deposition. So 6 vocab words that will certainly be popping back up. Make sure you have them on your I'm learning all this list. Y'all have any questions before we move to the second half of today? Yep. Sublimate, it's the actual, like solid to liquid is melting, solid to gas is sublimation. Just the description of the process. I'm going to be focusing on this part down here. All right, when I say the purple, it's this part in italics down here. The final topic of Unit 1 is density, which is probably also not a new word for you. But density refers to how much the particles of something are smashed together. And if they're really, really close together, like to the point where you're at a concert that you can't move around because everyone's so crowded, well, that means it's very, very dense. And if you look at the states of matter, which one's the most dense? Yeah, solids are the most dense based on their particle arrangement. So if solids are the most dense, the least dense would be the gases. All right, that's the concert that someone you've never heard of is playing, so it's really easy to move around. The particles and gases are further apart. There's a couple ways that we can look at density. One of them is conceptual. the other's mathematical, and we're going to do both. So let's start with conceptual. If you mix two items together with different densities, they'll separate eventually. And one of the whichever of the items is less dense will be on top. Here's a chemical fact about water. Bless you. Water has a density of 1. Water's density is 1. So here's some water. Again. We're going to drop some stuff in the water. Let's start with some rubber. Here's some 2 different sizes of rubber. Let's start with the big one. There's that big sample. What do you think the rubber will do in the water, float or sink? I have a lot of floats. What do you think at home? All right, here we go. So let's do a little test with the rubber. Here we go. Y'all suck at this game. It sank, but look, I have a little sample too. What do you think the little sample will do in the water, sink or float? How's it a trick question, man? I didn't like change my, I mean, it's whatever you think. Here we go. Let's try the little one. Here we go. Y'all, density is intensive. Remember that word from Friday? If something, you already wrote it down. You already wrote that down. If something's intensive, it's a property that doesn't change, even if the amount of matter changes. What that means is if something sinks in water, that type of substance always sinks in water. What might the density of the rubber be numerically? What could it be? It's sunk. Water's is 1. 2. What else? Ooh, 3. That was really creative. What else? Oh, now you're going crazy. Yeah. Any number above 1. We know it has to be something above 1 because water's is 1 and it's sinking. Therefore, it must be more dense. Now, we could figure out what this exact orange number is supposed to be, which will be what we're doing here in a few minutes. Let's try one more sample first. What's that? Yeah, it's cork. All right, we've got some cork here. All right, let's start with, let's go little cork. All right, got a little piece of cork, and we take the cork and float or sink. You might finally be right for the first time today. All right, hey, check it. It floats, but what if the cork, I'm gonna set the cork, ready for dinner. What if the cork gets big? What happens now? Because density is intensive, right? This is the reason why if you've ever been like hanging out near a river and you see like a twig float down the river and a few minutes later you see a tree float down the river, right? It's because if the twig is made of the same stuff as the tree, then they have to both float. What might the density of the cork be numerically? You're right, 0.5? Point what? 0.09? 0.00000 what? No, I'm just kidding. You're good. Yeah, any number less than 1, right? Okay. Let's move to the last idea then. Look at the very bottom of the opening slide that you already wrote. In red, you see your density equation. Look, here's me rewriting it. Density equals mass over volume. All right, that's a division sign that you wrote. I'm going to give you this formula on your test next week. You'll have a formula chart and a periodic table and stuff, and this will be on it. I'm going to give it to you. I'm not going to give you the other two forms of it, but you can manipulate this algebraically to get the other two. That's a 7th grade math skill, because you need to know how to get to those. Now, if you're bad at that, you have two choices. Come to tutoring and I'll show you how to do it, or just memorize the other two. But you do need to know all three. I'm only giving you the first. Steve used to writing, so I like you. For those at home, the students received this paper. These will be our last 3 examples that we work out together. Now, focus here. We're working together. Don't start working yet. I want you to look at the purple. All right. I've had some confusion today that I don't want you to have. The purple that you see on the opening slide lists the required units for each of the variables. What that means is that if you are inputting a mass, it has to be something that's in grams. If you're finding mass, it's going to get, the answer will be spit out in grams. But this is really critical info. All right, volume can be measured in milliliters or centimeters cubed, while density has the units together, right? It's grams per milliliter. Or it could also be grams per centimeter cubed. Either liter unit could be there. So you'll hear me referring back to the purple opening slide. That's what I'm talking about. All right, let's do this. I have a set protocol I go through for math in here. Some of y'all are really good at math, especially this kind of easy math we're doing, and you're going to think that I'm going pointlessly slow. But my step-by-step is really good for the harder math that we're going to do later. So I just start where I'm going to end. If you look at this first question, it wants us to find the density of a material with blah, blah numbers. What I'm going to do is extract the numbers with their units. So let's do that together. The first value I see is 26, and that's grams. The second value I see is 6.5, and that's centimeters cubed. And then I like to add a question mark to the bottom of my work because we're at school and they're certainly going to ask us to find something. Next, I'm going to equate these units to variables from the equation. Here's where that purple info from the opening slide can be helpful, because if you look there, it'll tell you that grams is units of mass, while centimeters cubed is units of what? Volume, right? It's labeled as volume on that opening slide. And if you're not real naturally quick at this, this is a good process to go through so you don't put a number in a wrong spot when you start to plug and chug. Finally, it says calculate the density, so I know that's what I'm looking for. You'll want to use the right form of the equation. You want to choose whichever one has the missing variable isolated, has it by itself. So we'll start with the main one. To find density, it's mass divided by volume. The mass is 26. The volume is 6.5. You have a calculator. Make sure you are plugging away with me. However, you need to watch your sig figs. They will haunt you all year long. Watch your sig figs and your units. Whatever number we come up with right here has to have perfect sig figs and then units after it, or the whole thing is wrong. Any brave souls want to throw a value out there? What'd you write? 4 is not good enough. 4.0 is not good enough. That's it. 4.00. What are the units? Grams per centimeters cubed. Because remember, those density units from the opening slide at the bottom in the purple can be grams per milliliter or grams per centimeter cubed. The reason I chose CM3 is because of the volume unit up here. But yeah, 4.00, right? Because 26.000 is 5 sig figs. 6.50 is 3 sig figs. And the smaller number wins. Ending zeros are significant if you can see a decimal. So be good at this. Would this item sink or float in water? It would sink, right? This problem doesn't tell you what the substance is, but we know if we drop it in water, it's sinking. Let's do another one together, but draw some cards. It says the density of a dreamlight, that sounds cool, is 20 grams per mil. Then it gives us a volume and asks for a mass. Let's extract some numbers from number 2. The first value I see is 20. The units is grams per mil. All right, the second value that I see is 4.09. Let's see if y'all can help me label some stuff. Let's go over to cluster 5. Yeah. C2. Hey, 5.2. What is grams per milliliters units of? Remember, your choices are density, mass, or volume. Density, perfect. Yep, just go back. Look at the opening slide. It tells you exactly what it is. Let's go over to cluster 2 and talk to C3. Hey, 2.3. What variable does milliliters connect to? Volume. And it wants us to find the mass. Everybody cool? Use the equation that has the unknown by itself. We're looking for mass. It's this one that says mass equals volume times density. So mass equals the volume times the density. I'm going to draw a card for the answer, so find it independently with good sig figs and units. right, sig figs in units. Hopefully you're feeling good. Let's go over to cluster 5 again. This time talk to seat 4. Aspen, it's you. Aspen, what'd you get? He said 81.8. Do you agree with that entire answer? What part do you not like? Just that. Yeah, mass is only measured in grams, so careful with your units. I heard someone complain about the sig figs, but the sig figs are actually good because this is 3 and this is 4, because ending zeros are significant if there's a decimal there. So 3 sig figs is the correct count. It's sandwiched. Yeah? All right, you do one by yourself and we will be done with the whole first unit of this stupid class. Take a few minutes, call me over if you get stuck. I'm going to point. Give me another 30 seconds while other people have a chance to realize it. Some of you have noticed the trick and some of y'all haven't. Look here regardless. Give me everyone's attention because there's a twist here. If you've just been running and going and getting close to the plug and chug, then good. I hope you know just how my steps work. But look here. You see that unit? There's a problem with that unit. Kilograms, if you go back to the opening purple, is an unacceptable unit. It's a mass. Only grams can go into the equation. Kilograms is no good. Now, it's an easy fix because you're so smart from last week that you know how to make kilograms become grams, because kilo is up here. Remember your unit sheet that you don't have to memorize? Kilo's up here and the base is down here. So to go from kilo to just grams, the unit's getting smaller. So what should that number do when you fix it? It should get bigger. The kilo exponent is a 3 down to a base of none. In other words, before you plug it into whatever equation you choose, this number needs to get bigger by 3 slides. Make this number bigger by 3 decimal slides, and then you'll have grams. I don't know if y'all could hear me. I forgot I was recording right there, but it's this unit right here that needs to be grams. So convert kilograms to grams before plugging and chugging. Another moment, looks like you're finishing up. Here we go. Check your work, check it out. Here's what I got. Here's my conversion of kilograms to grams. I identified this value as a density and this new value as my correct mass. I chose the volume equals version of the equation, which puts mass over density. 3 sig figs with proper units. Any questions? You want to watch the dry ice video? Yeah? You don't get to watch it at home. You should have been in class.